Greetings, traveler. I'm the calculus cleric, and today we're going to be doing some more work on limits. Mainly today we'll be exploring the correlation between function continuity and limits. Now, the question is to find the value of the constant a, b, or c that makes the function continuous. The function they give us is a piecewise function. Basically, it's a complicated function that they break up into separate parts to make it easier for us to graph and look at in terms of numbers. So instead of a single equation for a really complex graph, say one that looks like this, they'll simply break it up in terms of the x values, the domain of that function, and then they'll try to define it from there. For example, if I had a piecewise function that looked like this, instead of trying to make a single equation that describes this whole function, they'll break it apart into pieces. Let's say from here to here is 0 to 1 in terms of x. Here's infinity and here's negative infinity. They'll say from negative infinity to 0, it is defined as the function of this line. So let's say that's y is equal to 0. And from here to here is determined as the function of this line. So from 0 to 1, it's the function of, let's just say it's just ax plus b. Not the same ax plus b in the problem, but a different ax plus b. And from there, let's say this is equal to y is equal to 2 from 1 to infinity. Now, if you notice about this, is that these graphs aren't exactly continuous. And the way I can fix that to make these points defined and make it one seamless function is to use greater than or less than or equal to signs. And so we'll want an intersection here and an intersection there instead of the open circles that we currently have. So we just simply slap a greater than or equal to sign at the 0 and then a greater than or equal sign at the 1. It'll work if we do this as well or this even. And there's probably more combinations you can do with this as long as we don't have two greater than or equal to signs on the single point. It'll be fine. Okay, so that's just a little bit on piecewise functions. Now to the actual problem. What they're asking us to do is to make a continuous function. Like as we saw before, no breaks or interruptions, so no open circles, no jumps of any kind. We want a seamless function that's defined on all of its x values. So to do that, we'll have to take a closer look at the domains of each one of these equations. Now what you'll notice is that this contains a negative 1, and so does this. Now these line up perfectly because when x is less than negative 1, it'll be this equation. So it looks something like this. And as soon as it hits negative 1, it'll transition to ax plus b because x is greater than or equal to negative 1. Oh, maybe I should clear up a little bit this so you can see it better. As you can see, x is greater than or equal to negative 1. Because it had a greater than or equal to sign, although the equation x to the negative 1th power has had an open circle at that point, the ax plus b equation has a closed circle at that point, making this point defined. And what this is telling us is that at x is equal to negative 1, these two functions will have the function x to the negative 1, and ax plus b will have a solution at x is equal to negative 1. Basically, we can use this to set up an equation. Basically, we can use this to set up an equation. What we can do is use the principle that these two values have to equal to each other at x is equal to negative 1. So set up the equation x to the negative 1th power is equal to ax plus b when x is equal to negative 1. And what we can do is substitute negative 1 for x in this equation, which will give us this equation. And from here, we'll notice that although we got rid of the third variable, there is still two variables. If you remember, the rule for solving variables is that you have to have the number of equations equal to the number of variables in your equations. So because this has two variables, it also has to have two equations. Simple enough. So now we have to figure out a way on how to get a second equation. So now we will turn to the second part of the domain. If you'll notice, for the second and the third equations that are provided, they'll intersect at x is equal to 1 half. Because when ax plus b is less than or equal to 1 half, closed circle right there, it will transition into x to the negative 1th power. And even though that has an open circle, the ax plus b had a closed circle, so it's a defined point there, making that continuous. And it also tells us, once again, there's a solution at this point. Hence, we can make another equation in which we set the value of these two equal to each other. A second equation. So let me separate this by equation 1 and equation 2. And we'll plug in the point x is equal to 1 half, because only at 1 half do they equal each other. Plugging 1 half for x yields us this. So now we have two equations, and I'll write them over each other for the next step. And I'd like to clean this up a little bit and provide some additional explanation about what to do with those pesky negative 1 exponents. You'll see that here I already got rid of the negative 1 exponent that was supposed to be there. And the reason why is that because when there is a negative 1th power exponent attached, you take the reciprocal of that, which is simply you divide it by 1. Or a simpler explanation is that you just flip the number over. Hence, negative 1 over 1, but that's just equal to negative 1. So this remains the same. But now 1 half to negative 1 can simply and just reciprocal it from the beginning, which is 2. So our new set of equations will look like this. And now that we have two equations, we can solve for the two variables. What we can do is set up a system of equations here. And what I would like to do is I'd like to cancel out a variable. What we'll see is that there's a common variable here, plus b and plus b. But now to cancel them out, if we were to add these two equations to each other, we'd have to get one of these b's to be equal to a negative b. So because b minus b is equal to 0. And how we do that is we multiply one equation by negative 1. It doesn't matter which one, just pick one to do, because we don't want to multiply both by negative 1, otherwise we get negative 2b and not the value of 0 that we want. Remember that we have to keep the equation the same, so we have to multiply every single term by negative 1. And what this will do is it'll give us this system of equations. Plus b, negative 2 is equal to negative 1 half a minus b. And now when we add these two together, we'll get negative 3 is equal to negative 1 half negative 1. I'm solving for the coefficient of a is equal to negative 3, 2. Negative 3 over 2a, and the b's cancel. B negative b is 0. So now we can solve for the variable a. So I'd multiply both sides by 2/3. The 3's will cancel out here, and that'll give us negative 2 is equal to negative a. And you multiply both sides by negative 1 to cancel out the negative signs and isolate a by itself, which is a is equal to 2. Excellent. So we have our first variable, but remember we have to also get our second one, our b variable. So to do that, we'll simply replace one of our original equations. I'll choose negative 1 is equal to negative a plus b, simply because it doesn't have any fractions. We'll replace that with the answer we just found, which is a is equal to 2. We'll perform that substitution, And then we'll simply isolate the b variable. So we'd add 2 to both sides, which is 1. These two cancel out. Negative 2 plus 2 is 0. 1 is equal to b. A is equal to 2, and b is equal to 1.